All right, so in the last video, I gave a solution for the rotational worksheet, rotational dynamics worksheet 1, the last problem. And in that problem, we had a boy walking across a beam. And the question was how far can that boy walk before the beam starts to tip? And so when I was doing that problem, I chose the pivot point on the far left over here. And then I did my calculations and I went from there. But I realized after doing that, that I could choose a different pivot point that makes things a little bit simpler. And so that's what I'm going to do in this video, because remember, an important part about torque and static equilibrium is that if the object doesn't have a net torque on it, it doesn't matter where you choose the pivot point to be. So the first video, I chose it right here. In this video, I'm going to put it right there and just see what happens, see if I get the same answer. Now keep in mind, this only works when your net torques and your net forces are 0. If it's rotating, if it has a net torque on it, you can no longer do this. But in this case, it doesn't, and so we can. Now, the rationale behind choosing the pivot point, you might say, okay, well, how do I know? Like, how do I know where to put it to make my life easiest? Well, the answer is that if you have multiple forces acting on an object, you want to choose the pivot point so that it eliminates the most amount of forces as possible. In this case, no matter where we choose our pivot point, we can only eliminate one force, because all of our forces are at different points along this beam, and so you can only choose one force to eliminate. However, if you chose, in this case, I'm going to choose right over the second support as our force to eliminate. You'll notice in this problem that one thing about it is that the normal force at F1, this first support beam, is going to go to 0, right? Right, just as it starts to tip, that contact force on this first beam is going to go to 0. And so I realized if I choose the pivot point over F2, that's also going to go to 0. And you might think, well, how can you solve a problem if you have two different forces that are 0? Well, let's just see what happens then. So now my pivot point is over F2, so I'm going to calculate my net torque. And so we know that the force at F1 goes to 0, so I'm going to leave that off. So what forces do we have to consider then? We have to consider, and we also know the force at F2 is going to go to 0 because that's at the pivot point. So we have to consider the force of the beam and the force of the boy. So what is the force of the beam? And now let's be careful about what our signs are on these torques. If we have a force that would cause it to rotate counterclockwise, I'm going to call that positive. And if we have it, which would be the force of the beam, and if we have a force that would cause it to rotate clockwise, which would be the boy, I'm going to call that negative. Remember, it's totally up to you. I could switch those around as long as you're consistent about it. And you might say, like, well, how do you know which way each one's going to cause it to rotate? Well, just think about this pivot point. And if we were to erase all the forces but the one you're considering, so for instance, the force of the beam has a force pointing down, and it's just to the left of the pivot point, so it will cause it to rotate like this, and the boy will cause it to rotate like this. Now keep in mind, whenever we have a uniform distribution of mass, like this beam, we can consider all of the mass of the beam to be concentrated right in the middle of the beam. So that's an important property of torques and center of mass. So I can consider all of this beam, all of its mass, to be at the middle of the beam, which means it's at a distance of 2.5 meters from the end. And if this is at 3 meters, right, our pivot point, or our second support, is at 3 meters from the end, well then our radius, our distance between the pivot point and the support beam, is 0.5 meters. And so I have the force of the boy, or I'm sorry, the beam, times 0.5 meters, and I'll plug in the value for that in a second. And then I have minus the force of the boy, that's the force of the boy, times the radius, that's what we want to find. That's all equal to 0. Okay? Well, I'm going to plug in my values in. For the beam, I have mass times gravity. That's 40 times 10. And so I'm left with 40. Well, 40 times 10 is 400. Let me just put all the values in. 40 times 10 is 400. That's the force of the beam. times 0.5 is 200. So I'm left with 200. And I'm going to move this beam, or this force of the boy times the radius over to the other side. And so what is the force of the boy? Well, that's mass times gravity. His mass is 20 kilograms. And so 20 times 10 is 200. So I'm left with 200 times the radius r. All right, well then the radius is 1 meter. Wait, I get a different answer. My answer now is 1 meter, whereas my answer in the last video is 4 meters. How do I reconcile that? Well, think about where we chose our 0 point, or our pivot point to be. We chose our pivot point to be over the second support beam, which is located at a distance of 3 meters from the far left. And so what our radius is really telling us, it's saying it's 1 meter from this pivot point. And so 1 meter from this pivot point would mean it's at a distance of 4 meters from the far left. So really, we get the same answer. It's just a different numerical value for the radius because we've chosen a different coordinate system, a different 0 point. And so therefore, we still get the exact same answer as far as where is the boy on the beam. He's still a distance. I think actually I realized that the final answer wants the distance from the right side. So if the total beam is 5 meters long and he's out at 4 meters, that means he's 1 meter from the right side. But you'll notice that even though these are different numbers, it still represents the same point on the beam. And so the pivot point does not matter. You can choose whatever pivot point you want. And I realized that this pivot point makes it a little bit easier because now using this pivot point, I don't even have to worry about my net force being 0. I don't have 2 equations and you know, I don't have to solve that way. I can just simply use the torque equations to solve for my radius. All right, hope that helps.